Okay, so let's look at the second set of slides for today. So with this second set of slides, I'm starting the presentation of the second chapter. This is the chapter on specification and modeling of cyber-physical and embedded systems. The different boxes, like I just mentioned, are corresponding to the different chapters of the course. Chapter 3 will be on embedded system hardware, Chapter 4 on standard software, and then we are going to have chapters on evaluation and validation, on application mapping, on optimization. And in this particular course, there is no time, unfortunately, for the chapter on tests. That is something that we only have for another version of this course. So this means that there is a very clear structure for the remaining part of the course. So let's start to discuss considering specs and models. You will realize that we are going to discuss specifications and models in some detail. And the question is, why am I going to consider specifications and models at such level of detail? Well, I'm doing so because if there is something wrong with the specifications, then it's very likely that there will be something wrong with the final design. So starting with the wrong specs is a very safe way to really mess up everything and to waste a lot of time. So if you really definitely are not knowing what to do with your time, write a wrong specification, try to design from that, and then you have wasted a lot of time. So if you don't want to do this, you would better use a model of the system that you would like to design, and you would then need to use that model during all the design steps. Now, I've used the term model a number of times, and I think it's a good idea to try to define all the terms that are essential for the course. And therefore, I think it's a good idea to also define the term model. So what's a model anyway? I think there's a pretty good definition of this term by my colleague Axel Jansch. Axel wrote in his book in 2004, a model is a simplification of another entity, which can be a physical thing or another model. The model contains exactly those characteristics and properties of the modeled entity that are relevant for a given task. A model is minimal with respect to a task if it does not contain any other characteristics than those relevant for the task. So I think this definition very clearly demonstrates that there must be some difference between the real thing and the model. We will not always capture all the properties of the real thing in our model. We are designing a model so that we can use this in the design procedure, but there will always be some abstraction. There will always be something that we are not really including our model. Now, in our course, we will be looking at models, and before I'm actually talking about some specific models, I'd like to make sure that we understand the requirements that we have for models. In general, it's a good idea to start with the requirements first so that we are not designing our modeling approaches in the wrong direction. So which requirements do we have for modeling? The first requirement for modeling is resulting from a very essential limitation of human beings, at least of all the human beings that I know of. The human beings that I know have a very essential limitation. Humans are typically not able to understand systems that comprise significantly more than 5 objects. So if you really have to understand all the interactions between systems that are comprised of many objects, you will have lots of problems. So therefore, we have to deal with that problem. And one way out of that is to introduce hierarchy. which means that we model a system as something consisting of subsystems, and these subsystems in turn consist of subsystems, etc. So we have several levels of hierarchy there, and we use typically hierarchy in combination with abstraction. That means at each of these levels we are considering the model objects in a certain abstracted way. If we look a little more closely and if we think about Geiski's Y chart in this context, we come to the conclusion that there are actually different types of hierarchy. There is what people call a behavioral hierarchy, and in this context we're using objects such as states, processes, procedures as components, and there is a structural hierarchy. In this case we are referring to processes, racks, printed circuit boards, for example, as components. I'm not looking at geometrical hierarchies, so that's something that I'm skipping here because I'm not going to that level. So if we look at the requirements that we have for specification techniques, there is a second requirement that is actually a consequence of the first requirement. The first requirement made us introduce certain components, and now we have to consider the fact that we have to work with components. We must design systems from components. We cannot start from scratch every time that we are doing something, so we have to assume that there are some pre-designed components that must be taken into account. So one requirement resulting from this is that it must be easy to derive the overall behavior from the behavior of subsystems. So if we compose systems of subsystems, it should not happen that something very catastrophically happens. So if you add, for example, a CD player to your car should not behave in a completely unexpected way. Yeah? So that's something that we require. And in general, this means that we have to have techniques that will allow us to generate the overall behavior from the behavior of the subcomponents, and there has been quite some research work in that direction by researchers such as Sifakis, Thiele, Ernst, etc. Also, as a result, from the introduction of components, we have to model concurrency, because these different components over here, they are operating at the same time. Certain operations are going on in an overlapping fashion, so we have concurrency there, and we have to model this concurrency. But these operations are not completely independent. From time to time, these operations have to be synchronized, and we have to communicate between these different components here. There is a third requirement resulting from the type of systems that we want to model, and this is the fact that we need to model timing behavior. We know that timing behavior is very essential for embedded and cyber-physical systems. Therefore, additional information like periods, dependencies, scenarios, use cases are welcome, and also we need a precise model of the timing of the underlying platform. Once again, I think we cannot overemphasize the importance of this, because this has far-reaching consequences. Now, unfortunately, if we look at the theory in computer science, we get the impression that the theory in computer science has been developed into a different direction. Because in computer science, people typically work with a very abstract timing model. And they also work with a specific model of computation. If we compare this to the need of what we would like to have in embedded system modeling, we see that there is a serious deficiency. And this deficiency was mentioned by Edward Lee in a very famous statement that he made. He wrote, "The lack of timing in the core abstraction of computer science is a flaw from the perspective of embedded software." So there is a serious problem there. If we would like to look a little closer there, one question might be, what do we want to use timing models for? And in this case, I'm referring to Alan Burns for an answer. Burns wrote back in 1990 that we need timing specifications for 4 different purposes. First of all, we would like to measure elapsed time. So that is corresponding to a stopwatch. So whenever we run software, we would possibly like to know how much time has elapsed. So in our software, we would like to have the corresponding feature to a stopwatch. The second purpose is a means to delay processes or to have to put processes asleep for some time, and we would like to be able to specify that amount of time. And there are 2 more contexts in which we would like to specify timing. The third one, the overall third one, is the possibility to specify timeouts. There are situations in which we would like to react if, for example, a certain event did not take place for quite some time. We might be in a state, let's say for 20 milliseconds, and if we are in that state for 20 milliseconds, and if some event A does not happen in these 20 milliseconds, we would like to have a transition into some other state where we handle the fact that there was no event A in that amount of time. And there is a fourth context in which we would like to specify some timing. There are certain situations in which we would like to specify deadlines. That means we would like to make sure that software finishes in a certain amount of time. So these are some different ways in which we would like to use time in our specifications. There are more requirements for our specification techniques, again resulting from the characteristics of cyber-physical and embedded systems. I mentioned that these systems are typically reactive systems and that states are very essential to the modeling of such systems. So therefore, we would like to describe a state-oriented behavior. That means automata are pretty good models for our modeling. However, classical automata are insufficient. For example, they do not provide us with hierarchy. Obviously, there is no hierarchy in this diagram, so therefore classical automata are not sufficient. Also, we require some event handling. Events can be internal or external events. These labels M and K, they denote events which can be generated either in the information processing part, or they could also be generated in the physical environment. We do not really need to distinguish in our models very strictly between these two. Also, we would like to have a way to denote exception-oriented behavior. We know that for these systems, we must make sure that they work under all circumstances, and that means we have to plan for exceptions. So it's not acceptable if we just have a blue screen like for Windows, but there should be a planned reaction in case something goes drastically wrong. And we have to have an easy way of specifying this. So for example, in this little diagram, this event K could correspond to an exception. And we see already that the way that we have to specify this exception is pretty inconvenient, because we have to put this label to quite a number of edges. We will see a little later on how we can replace all these edges, how we can replace all the labels by a single one if we have an appropriate extension of our techniques for modeling automata. Now there's a quite long list for additional requirements for specification and modeling techniques. Like, for example, it would be very convenient to have programming language elements available. We know that for specifying complex algorithms, recursions, loops, etc. are very convenient. Also, it would be nice to have executability, which means that we would like to execute our specifications, because when we write down the specification, we are never really sure whether what we wrote down is really what we want to have. So therefore, it's very nice if we can simulate our specification and can check this against our intentions to make sure that we really specified what we want to have. Then furthermore, we saw that the embedded systems also become larger and larger, so therefore we need support for the design of large systems. And we know by experience that object orientation is pretty good for that, and therefore we would like to have object orientation as well. Furthermore, we would like to have domain-specific support. If, for example, we design a smart building, we would like to have some built-in terms in our modeling approach. So we would like to have built-in terms such as walls and rooms and floors, etc. It would be very inconvenient if we had to define everything from scratch. And the next item refers to the fact that the best specification technique would be pretty useless if the specifications would be completely unreadable. So therefore, we need to have a readable specification. Doing the specification in hexadecimal numbers would not be very nice. Furthermore, if we did one specification, we would like to reuse it, we would like to adapt it to a different scenario, and therefore it would be nice to have a specification which is portable and flexible so that we can use it for the next design as well. Then we may have certain threads, certain processes, and it would help to verify the overall system if we were sure that certain threads, certain processes actually terminate, so that would give us a certain confidence or design. Then there are certain non-standard devices like switches, like displays, like other I/O interfaces, and we would like to get support for these. And the list of requirements gets longer and longer, and the next one is the next entry in this list is actually an entry that I think demonstrates that there is hardly any hope to get specification techniques that are really perfect, because we would like to also specify non-functional properties like disposability, user-friendliness, and I think you can imagine it's very difficult to formally specify user-friendliness, so that's something that usually is very difficult. We would like to support the design of dependable systems, which again is very difficult. We know that we are going for efficient implementations, and we would not like to have any obstacles there. And finally, and that's the last entry over here, we need to have an adequate model of computation. For implementing the embedded system part of our overall system, we need to use an appropriate model of computation. We will see later on that the standard imperative model of computation has certain deficiencies, and that especially in this context it would make sense to have a different model of computation. So therefore we have to think about what it really means to compute in this context. So in a sense we are looking at the abacus as one particular model of computation. Edward Lee stressed the fact that according to his opinion, and he stressed this in a very easy to remember way, that in his opinion that certain developments in computer science went into the wrong direction if we consider applications in embedded systems. Because we know that in computer science the notion of computability has been discussed. This means that we are looking at some kind of more or less imperative program where we raise the question, well, will this program ever terminate? Now, Edward mentioned that there is a problem in this context, and he wrote the following: even the core notion of computable is at odds with the requirements of embedded software. In this notion, useful computation terminates, but termination is undecidable. In embedded software, termination is failure, and yet to get the predictable timing, subcomputations must decidedly terminate. What is needed is nearly a reinvention of computer science. So that's a really very drastic statement. And it really refers to the fact that what we call computable in computer science is really not matching very well with the needs for embedded software. Because there we assume that the software is running more or less forever, as long as there is power, as long as there is electrical energy. So such a system should be designed that it does not terminate by itself. But on the other hand, we need to decidedly figure out whether certain computations will terminate, because otherwise there is no hope to prove certain timing guarantees. So for that reason, we're looking at other ways of modeling systems, and that means we're looking for what we call non-thread-based models of computation, because these problems are essentially problems with von Neumann or thread-based computing. So we are looking at other models of computation. And this leads to the question, what's actually a model of computation? What does it mean to compute? So if you look at the literature, you will find that people are referring to two things when they talk about models of computation. And the first thing is the component and an execution model for the different components that we have in our system. And the second thing is the communication model, which describes how we communicate between these different components over here. And we really have to distinguish between what goes on in the computations and what goes on as far as communication is concerned. So if we look at the different components here, it's usually very convenient to be able to describe relations between these components. And these relations are captured as so-called dependence graphs, which later will be called task graphs. So in this task graphs, we have certain nodes. These nodes could be programs or simple operations. And we have relations between these nodes in this graph. And the overall structure is called a dependence graph. Formally, a dependence graph is a directed graph in which a subset of the cross product of the nodes is a relation. And in this context, we are defining immediate predecessors and immediate successors. So if there is an edge from one node to some other node, then the first node is said to be a predecessor of the second, and the second node is called a successor of the first. Now we also model indirect reachability there in this graph. So if we have one node that can be reached from some other node, then the second node or the reached node is called the successor node, and the node from which we can reach the successor node is called the predecessor node. And in this case, we are also considering indirect paths from one node to the other. Formally, we are calling this the transitive closure of this subset of the cross product. In these dependence graphs, we would very frequently like to add more information. So for example, we might want to add timing information there. And this would be one standard way of annotating timing information there. The first entry in this tuple denotes the arrival time. That means starting at that particular time, we are able to perform the computations in that node. And the second entry in the tuple denotes the deadline. That means the time by when these computations should be done. We can add more information to these dependence graphs. In many cases, it's useful to add I/O information as well. We would like to indicate explicitly that some I/O is required. So this node over here explicitly states that there is some input required for that computation that's performed by this T1, and it's the same over here. And obviously, this computation T3 is generating some information that has to be made available at the output. And there is more information that we can add there, like information about shared resources. How do you like my gimmicks there? There are some shared resources. So shared resources can be, for example, memory, which certain computations are sharing, or there can be shared I/O devices, and we can explicitly indicate this in the dependence graph. There may be special cases of dependence graphs where we are looking at periodic schedules if we have a system which is running forever. then we will most likely have periodic schedules, like if we have, let's say, an MP filter, MP3 filter, then we will have computations that go on forever, hopefully, as long as there is energy. And then we also need to denote the computations there for this processing of MP3 music. And one way, or the appropriate way, would be to use infinite dependence graphs. In these infinite dependence graphs, we have particular instances of computations, and each of these instances would be called a job. We need to do the same computation again and again, and if we explicitly indicate each execution, we would then arrive at infinite dependence graphs. So these periodic dependence graphs would be infinite. We saw that we need to model hierarchy, and this is also reflected in our approach to modeling dependence graphs. There can be hierarchy in dependence graphs. So, for example, this would be a hierarchical dependence graph. Are there any questions with respect to that so far? Anything where you need to stop me, where you need to slow me down? Okay, not so far. Maybe in the offline part of the lecture. Okay, so let's look a little more closely at what I called a model of computation. So in such a model of computation, we realized we need to have a model of the computations in the components, and we need to be able to communicate. So with respect to communication, we will distinguish between essentially two kinds of communication. The first kind is called shared memory. Shared memory-based communication is visualized on this slide, where you see two components, and we assume that these two components have access to some shared memory, and they can send some information there to the shared memory, and they can read some information there to the shared memory. That means there may be variables that are accessible to all the different components there. Unfortunately, shared memory-based communication is mostly restricted to local systems, because if we will try to use shared memory-based communication in a distributed system, let's say in a system which is distributed over several different continents, this way of communication would be very slow because it would take some time for the variables actually to propagate into these memories, so all updates would require quite some time. Now, for shared memory-based communication, there is one specific problem. And this is the problem that there may be some rather unexpected behavior resulting from the use of shared memory. And in order to demonstrate this, I would like to use a little example. Let's assume that we have two little programs, or more precisely, I would call these two little pieces of program threads. These are two sequentially executed sequences of instructions, and there is the thread A and the thread B. In the thread A, we are assigning some initial value to some variable, and then for the time being, we assume that this gray part is not present in our code. Then there may be an if statement, and if the value of u is less than 5, we can possibly increment that value, and there may be some remaining code. And there is some other thread where we would set this variable u to 5, and we assume that u is a global variable. Now, in order to demonstrate the type of unexpected behavior that can happen, I'd like to mention the following. It can happen that in this context, if we are not using the gray code, that u would be set to a value of 6, which would be somehow unexpected, because over here we are explicitly testing whether u is less than 5. So if it's less than 5, we assume that it at most could be set to 6. That at most it could be set to 5, sorry. But it can happen that first we execute this piece of code until we have tested the value of u, And then there could be a context switch to the other thread, and the other thread would get executed. We would set that variable to a value of 5, and then there could be a context switch back to the first code, and at that time we would set u to 6, which would be rather unexpected. So this type of behavior is something that people typically don't like. So therefore, we have to restrict the ways in which these threads get executed, and we can do this by introducing so-called semaphores. Semaphores are data structures on which certain operations are defined. In particular, there are operations called P of S and V of S. And for P of S, we can grant concurrent access to some protected resource, to some resource protected by the semaphore S. And in general, we can grant up to n concurrent accesses to that resource. In our course, in my course, we will just be considering the case of n equals 1, where we could call these corresponding operations mutexes. That means that we can use these operations to make sure that only one of the threads is actually getting access to some protected resource. And then V of S is increasing the number of allowed accesses to the resource. So if we would actually use this gray code over here, then this unexpected behavior could not happen because we would protect this part of the code, which is actually called a critical section. It's a critical section because it contains accesses to shared resources. And if we make sure that only one of the two threads gets access to this shared resource, then this unexpected behavior cannot happen. So therefore, the thread-based or imperative model should be supported by mutual exclusion for these kinds of critical sections. Now that was the first type of communication between the models. The second type of communication is called message passing, and we will see that there are actually two classes of message passing. The first class of message passing is called non-blocking or asynchronous message passing. For asynchronous message passing, the sender does not have to wait until a message has arrived. In this situation, we might have a sender, and the sender wants to send some information. This information gets sent to the recipient, but even before the recipient is actually using that information, the sender can proceed. The sender can proceed immediately. If we look at this from the point of view of the corresponding information there in some kind of buffer, we see that initially this information is just sent to some buffer, which is typically implemented as a FIFO buffer, and it may happen that actually we store several packets of information there in the FIFO buffer before the recipient is processing the first entry there in the FIFO buffer. On the other hand, there may be a second variant of message passing called blocking or synchronous message passing, sometimes also called rendezvous. In this case, the sender will have to wait until the receiver or recipient has received the message, which means that we assume that the sender is sending this information. This information is sent to the recipient, and now the sender has to wait until the recipient has actually also noticed that this information has arrived. The recipient will then send an acknowledge to the sender, and at that point in time, the sender could proceed. In this case, we need no buffer in between these two components, which means there can also be no buffer overflow, but obviously the performance is reduced because obviously the sender has to wait until the recipient is capable of accepting that information. Now these are the kinds of communication that I would like to mention in the course. There are possibly also other types of communication, Like, for example, if we include some advanced knowledge in physics, if we look at quantum mechanics, for example, there is a mechanism called entangled states, and with entangled states we can communicate over a certain distance, and this type of communication would not correspond to anything that I've mentioned so far, but we will not talk about the entangled states any further in this course. So there are these two types of communication. One of them is actually partitioned into two subtypes. These are the types of communication that I'm considering in this course. Okay, so this is the animation corresponding to the flow there. So this is what I wanted to explain with respect to the communication between these components here. We also need to look at the different ways in which we model the computations within the components. And for this, we have several possibilities. The first being the use of finite state machines. I did already mention that finite state machines are a very appropriate model. We know that we are talking about reactive systems, so therefore using finite state machines is a very appropriate way. And we could think of using the finite state machine model for the components, and in general we will have several finite state machines, and in general we will have some communication between these finite state machines, which means that we will be talking about communicating finite state machines. As a second option, we might be using so-called discrete event models. In a discrete event model, we are using a certain queue, a queue where we have stored certain entries, and in these entries we have a time and we have a certain action. So each of these entries has a time field and an action field, and these entries would typically be sorted by the time at which the action should happen. And then the operation of such a discrete event model, or the simulation semantics of such a discrete event model, is typically explained by assuming that we pick one entry, the youngest entry, there in the queue, and performing the action which is indicated there. So in this particular case, we would be setting variable a to a value of 5. We would be picking the next entry there. We would be setting this variable b to 7. We would be picking the next entry, and we would be assigning variable c to a value of 8. And then we would reassign variable a to 6. And some of these entries might also include the generation of new entries in this queue. And once again, this queue is usually sorted by the time at which a certain action should happen. And the generation of entries there could also include a specific time at which such a new action should be performed. So that's what we call a discrete event model, and we will see during this chapter that we are using discrete event models in certain contexts. Then there's the third type of model that we can use there within the components. I'd like to mention the von Neumann model, which is the standard model of computation that most of you are using whenever you're writing a program in a standard language such as C or C++ or Java. There you assume that unless something else is explicitly indicated, that you have a sequential execution, that you have a program memory, that you have a memory for variables, that variables can be reassigned again and again. All these are parts of the so-called von Neumann model, and we may have a number of threads that we are executing in such a von Neumann model, and usually we also assume that there are some global variables, and we have seen all the problems resulting from the use of global variables. Now, if we look at the cyber-physical context, we realize that there are also other ways in which we could describe the local behavior there in the components. We could, for example, use partial differential equations. So if we have a physical system such as a car, which is jumping up and down on a very bumpy road, like in this animation, then it's very useful to use partial differential equations to describe the movement of the car there. It would be very inconvenient to be constrained to the use of, let's say, discrete event systems. It would be much more convenient to be able to use partial differential equations here. There are other ways in which we could describe the operation within the components, like a so-called data flow model, where we would be modeling like the way in which data flows in a distributed system. We will see later on during the course examples of such data flow models. Also, we can be using Petri nets, which are models that focus on dependencies between certain activities. If the focus is just on dependencies, then Petri nets are in many cases more convenient than other models, like, for example, data flow models. So we see that there are quite a number of ways in which we can describe the computations in these components. Now, overall, this leads to the following classification, a classification which I'm using to structure especially the content of this second chapter of the course. In this classification, you see two dimensions. In the horizontal dimension, you see the technique that we're using for communication. You see there shared memory and you see message passing. And for message passing, we are distinguishing between synchronous and asynchronous message passing. And then in the other dimension, we see the computational model that we are using in the components. And there you see that we have as entries communicating finite state machines. We have data flow. That was something that I just mentioned. We have Petri nets. We have the discrete event model. And we have the von Neumann model. And then within this table for the various entries, we have particular examples. And from my point of view, it's very useful to identify particular languages with particular entries there, with particular places there in this table. So for example, a very popular language called state charts is based on the combination of shared memory with communicating finite state machines. And we will also see a little later on that a very popular language called SDL is based on the combination of asynchronous message passing with communicating finite state machines. And then we see that for data flow, it's not very useful, at least I can't really imagine how it could be useful to use shared memory there. But we are going to see some other models that are used in this context. We are going to see Kahn process networks, and we are going to see synchronous data flow models as entries there in this table. Then for Petri nets, again, we have a situation where shared memory is less useful. Mostly we are based on message passing, and we have different variants of Petri nets. Then for the discrete event model, it's a little more difficult to say, because for the discrete event model, we can have models that actually are models of systems using shared memory, and we also have models of systems that are using message passing. But in order more or less to fill these available places here in this table in a meaningful way, I looked at the way in which these discrete event models are typically implemented. And these discrete event models, simulators based on discrete event models, usually are implemented with shared memory, because we have seen this queue. In this queue, we have these entries, and it's very difficult to implement this queue in a distributed fashion. So simulating discrete event models in a distributed fashion is a very difficult task, and typically simulators simulating systems based on a discrete event model are using a single processor, and everything is in a way then shared and localized to one memory. So therefore, all the languages that are using the discrete event model have been entered in this place over here in the table, and that includes, as special cases, hardware description languages such as VHDL, Verilog, and System-C. And for a distributed implementation, we only have experimental models. The problem there is simulators in that domain are typically very slow. And then we have, as for the next line, the von Neumann model, where we have all the languages that you normally know. So that means C, C++, Java, and you name the language, and I will typically tell you that this is also a language which belongs to this row in the table. Now, if we would like to implement message passing with the standard imperative languages, we would usually use libraries. For C++, C, we can use libraries for message passing. There are a few languages that have a particular way of message passing built into the language. CSP and Ada are two languages that have synchronous message passing built into the language. So this leads me to the summary of today's lecture. I started out presenting this set of slides by first trying to collect and enumerate the different requirements that we would like to meet with specification and modeling techniques. And we saw that there is a huge set of requirements that we have for our modeling techniques. The first one was the need to model hierarchy, and you might remember the very long list. The last one was to use an appropriate model of computation. And this led to the discussion of models of computation, where we saw that as a kind of byproduct, we came to discuss dependence graphs, which have been different here. And then we are considering models of communication between the different components there. We saw as special cases shared memory and message passing. And we also looked at models for the computation within the components. And there we saw as examples models based on finite state machines and on discrete event systems, and also some others. We are going to use that table, the table on the previous slide, in order to structure our discussion in this chapter 2. And we will go through the different entries there in this table during our discussion of chapter 2. So are there any questions at this time?